is Dr. Raul Camposano from Sage Design Automation. Raul comes with a lot of experience in design rules, and his first slide is a bio, so I'll let him do that. Raul, would you like to get started? And you'll have to hold your mic if you want to stand.
Hello? Oh, yeah. I work with a company called Sage Design Automation. We're a small startup. We're here, right? And we're developing a design rule management platform. And the reason we're doing that is that in the old days, if you look at an 200, 300, 500 nanometer design manual, right, it was a thing that was fairly thin. You had a order of 50, perhaps 100 rules. Half the pages were revisions, right? You changed what, when, right? And then there were a bunch of rules at the end. But that has changed. Now you have thousands of rules, right? If you believe people that are looking to the future, right, you may have tens of thousands. And furthermore, the rules have become much more difficult. So that's what I want to talk about. So the first problem is just the number of rules, right? And the number of rules, if you look at that, right, we put that together from information that we have. There was also something on the Synopsys website. At some point has grown to 10,000 roughly. That is the order of magnitude. Now, that is a little bit overblown, because if you look at it, there's a lot of rules that are very simple and repetitive, right? And they just repeat on different layers of metal, etc. The second thing is that a lot of the stuff gets derived actually from the design rule decks, not from the number of actual rules. So there's a lot of invented layers, right, that you have to put in there to write the deck, right, to do all the operations. So the real number of rules is a little bit smaller than what you see there. It's overblown, but still, you have to administer of the order of 10,000 rules. Now, from the point of view of writing a system to do that, right, if you're a computer scientist, that's pretty trivial, right? Databases today contain trillions of objects, and you shouldn't have any problem of keeping track of 10,000 objects. So the number is actually not the problem, right? And the other thing is that is often cited is you have to check the things. You have to run design rule checks, right? You have to write text files and go to the routers to generate the stuff. All that parallelizes reasonably well. Memory size in computers is the one thing that has kept track. You can get machines today with a terabyte of memory, right? And so that all works reasonably well. So the number by itself, right, even though it looks intimidating, is not an issue if you automate. It's hard to do this by hand, like in the old days, meaning you write a manual in Word with a bunch of PowerPoint pictures and then hand it over, right? But if you automate this, it's actually not a big deal. Next. The second problem, and that may be a little bit more difficult, right, is the actual complexity of the rules, right? Rules have evolved from simple overlaps, distances, width, and things like that, to much more complicated things where you have to take into account connectivity. Rules are becoming less local. Some of them you could even call patterns. They're not rules anymore, right? There's a lot of objects involved in this. That has to do with lithography, with double, triple, perhaps quadruple patterning at some point. Etc. And so what we do there is we have an approach in which you can enter these rules graphically, and then you can execute them right away, meaning you don't have to write a separate deck. There's a design rule checker included in the system, so as you draw and write equations, right, you say this has to be bigger than this, and you write it in a formal, unequivocal way, you can go and check directly. So that is one thing. So you develop the rules, like you develop a program interactively by checking them right away. You can run them immediately, right? And the second thing is you can generate patterns, right? People want to visualize the rules, and they want to know what is a pattern that fails, what is a pattern that passes. And we can generate these patterns. We can even generate coverage numbers, right, for these patterns, and then run third-party tools to see if the deck that you wrote, if you need something like that, indeed is indeed written correctly. And so I want to finish with just saying that design rule complexity can be traded because we have coloring, right? Because we have cut masks, right, and other things. these things are very often not exposed to the designers, and it generates an additional level of complexity. So, for example, if you would have cut masks, right, the design rules for cut masks, which you see there on the right, are fairly straightforward and simple. But if you look at what the person that is designing sees, right, and they're just doing this meta layers, they perhaps are not even aware that you have double exposure or cut masks and things like that. And so they get a fairly complicated rule that is a little bit more difficult, right? And you have to develop these things to tell the tools that very often are not aware of all this post-processing that happens, right? And so this has been taken into account as well. Thank you.
Thank you, Raul. So there'll be time for questions at the very end, so we're going to have all three panelists speak first, and then we're going to take questions. Our next speaker is Mike Willett from Texas Instruments.
Okay. Hello. My slides up here. So I'm Michael Willett. I work for Texas Instruments in our physical verification for the CMOS technology nodes. I've been in physical verification for the last 10 years. Probably my primary area is the CMOS voltage dependent spacing DRC run set for the development and the related device voltage checker flows, and also for the LVS run set. The previous 8 years I was in physical architecture, doing I/O architecture development and ESD structure implementation, as well as some standard cell architecture design careabouts. So when we get, just like Raul was saying, with the insanity of the DRC checking at 10 nanometers, the double or triple patterning gives, for each metal and via layer, you need basically 3 mask reticles designated by colors. Those, it's up relatively about 3 times more of the rules to define the spacing allowed for each color and the proximity to the other colors. So you also have interaction between those metal and via layers. So you could have rules for how much overlap for the different colors or spacing of the different vias to the different color layers. And then there's questions, what do you do when the metal turns 90 degrees? Sometimes you have some particular careabouts with those colors. And if you have 2 different metal color lines, stitching them together can be problematic for DRC checking. How do you define where they can be stitched together, and what are the rules around those? So, and then there's questions about what you're looking at, the coloring for minimum metal pitch, but at what point do you not have to worry about the coloring and the different patterning for the 3 different colors? So at what point does that not be a concern? And then at what elevated voltages? What elevated voltages can those different metal layers handle? Let's go on to the next slide. So what I see for all these different rules, it's a challenge for us as writers to write all these rules and comprehend, but then for the designers to be able to check them and to understand how to resolve these implications that these rules have on their designs. That's where, like Raul was saying, something that checks the design as you're drawing it becomes a very important part for the designer to design their layouts, because they need to be able to get to a correct layout the first time and efficiently fix those DRC errors without having so many iterations in the design rule checking flow. The learning curve for the designers, it can become significant, trying to understand and comprehend this new set of rules that they have to know about. It's not as simple as just drawing one metal layer and running the design rule checks. So that's where the opportunities for smarter software techniques come in, to display errors such that the designers can make the smart corrections without having to move too many different vias and metal lines to to make it a efficient design. So then you also have to think about what are the design cycle and trade-offs that you can make with your design rules, because you have the option to design your design rules such that you don't have to give so much leeway for the designers to make mistakes that need to be corrected. So you could probably set some limitations on those rules to make the rules a little bit less complicated for the designers. But it's interesting, it's challenging, it's exciting to go into some of these advanced nodes and see what we can accomplish.
Our last speaker is Dave Dolman from Qualcomm. Boy, Dave.
Everywhere.
Yeah, you got a book out and everything, right?
Indeed.
So take it away.
Okay. I'm Dave Doman, and I speak way too loud. Like you said, that's my book. My kids call that the Pink Floyd.
Up here.
I'm way okay. Can you guys hear me? Okay. That's my book. My kids call that the Pink Floyd Dark Side of the Moon cover. Yeah. I've long since, I've been in the industry 35 years. I've long since got to the point where standard cells that I'm designing, flip-flops that I'm designing that fit inside the via of the first standard cells that I was doing. So I can point back to cutting acetate. So I'm old as dinosaurs, I guess. Enough about me. By the way, that's a good book. Feel free to go buy one. Okay. I want to talk about, I'm going to sound like I'm repetitive with what has been said so far, but I want to approach coloring by a different format. It sounds like a lot of the design rules that potential companies are doing deal with layout that's colored already. The problem that we've seen at Globalfoundries when we are pushing the technology is that limits the area. So you're going to see, with all due respect, you're going to see a lot of people doing colorless design and then going back and asking the EDA vendors to come in and develop coloring as going forward. Well, AB coloring, two colors is fantastic. That's a well-known commodity. But when you go to triple and quad coloring, well, I'm not a mathematician, but I used to say that that was an NP complete problem until one day a mathematician in the audience said, no, it's not. So I stopped saying that, and then a month later a mathematician in the audience said, yes, it is. So I don't know if it's NP complete or not, but it's very difficult. And every solution I've seen so far is heuristic based and eventually breaks. So my concern to all the EDA vendors here is give me better triple coloring and quad coloring. For those of you that have done standard cell layout, especially fixed poly pitch, this pattern over here on the right that's drawn, that is in every flip-flop you've ever done, or every latch you've ever done. Problem with it is that, especially the curves on the side, those curves don't shrink with technology. Hence, they get further and further. They eat into this corner and this corner further and further, which limits the size of the standard cell flip-flop that you can make. So that's another problem that you have, limiting area. I just want to point out that's an issue that we need to deal with. A way around it is to start doing single direction metal layout. But to do that, you're going to have issues with extra layers and vias, which are going to affect parasitics for your flip-flops and for your basic design. So you're trading off area versus performance, acres of silicon versus fortnights of time. Additional issues here are wide wires. All these wires inside your design are all min wires. Your rails, like the green at the bottom, that might be a 3x or a 5x wire. You have litho problems that you're going to need to deal with there. Let's go to the next page. I tried to hide the issue by just calling it design rule 1 versus design rule 2, but basically there's a strong trade-off between design rules that you can have trade-offs up here way above your fab capability, or you have trade-offs that are way below there. So there are issues that you need to deal with on that point too. And the thing is, there are reasons why you want to be down on the lower right corner of this curve. Unfortunately, you can't. I can't go into what those reasons are here, or I'd have to shoot you all. So, but trust me, those are issues that you're going to have. Let's go on to the last foil. Like I was saying, there are coloring issues with self-aligned double pattern, self-aligned quad pattern, self-aligned triple pattern between them. There's issues with routing of other signals that you normally wouldn't have, for instance in FDSOI with back biasing and stuff like that. You need to deal with issues like that. Special constructs. Standard cells, contrary to popular belief, are not straight DRC clean anymore. You have special constructs for a cross couple here, a via connection there. Those special constructs, layout people hate, process people hate, but if you want a good area issue, you're going to have special constructs to handle. The last issue I want to talk about is actually one that Dr. Raul was sort of kind of pointing out earlier in the one foil where he had the picture of the cut spaces. You're going to start seeing 10 nanometers, 14 nanometers, and below, you're going to start seeing features that appear on silicon that are not drawn. You have cut layers, like Dr. Raul showed it. You have mandrels that, because drawing edges of your back end is more important than the actual circuit or the metal. So you have features there that you can have spacing violations on, width violations on, min area violations on, that you're not drawing. And you need an EDA company to come show you an easy way to recognize there's a DRC issue here that's not drawn, but it's due to something you did over here. Those are things that I think we need to get some additional help with from the various EDA companies around. I basically am done talking, so I'll stop waxing poetic.
So we have time for questions now. I'm going to take the opportunity to ask the first two. So we talked about voltage dependent spacing rules with you, Mike, and before. What are elevated voltages nowadays? 1 volt, 3 volts, or 5 volts? What are you talking about when you say elevated voltages?
Elevated voltages are basically any voltage that's above your core nominal voltage for the design process. Usually it's for analog interface circuits or I/O circuitry. But it can be, typically it's up to 3.5 or sometimes to 5 volts. Or if you're in a flash specific node, it can get up to 13. 13 volts. 13 volts.
Okay. So one more question for you, Dave. You mentioned DRC errors, either spacing, width, or area errors on non-user drawn shapes. So is this reticle enhancement technology? What are these things that are not user drawn but cause DRC errors?
Okay. Well, basically, is what I alluded to when I was standing. It's mandrels, which is basically the edges of your back end of line versus the actual back end of line, or it's cut shapes for when you're going from like a 3x wire to a 1x wire, or a 3x to a 5x, which you will find in not just with power routes and stuff like that, but also inside of analog mixed signal, where you have special routing needs going from a digital part to an analog part. So it's issues like that, but that's just the beginning. That's the edge of the envelope. There's far more complicated stuff down at 7 nanometers and down there, but hopefully we'll have EDA solutions to recognizing those DRC issues long before that gets out where people are actually doing 7 nanometer design.
Okay, thank you. I'm going to open it to questions from the audience. Would you please state your name and your company affiliation, and then you ask your question to either one of the panelists, or you can direct it to the entire panel, and then the person who's feels most motivated to talk about that topic can give the answer to the question. Any questions from the audience, please? Your name and company.
Hello, my name is Frank. I'm from Qualcomm. Hey, I have a question for Mike. So you talk about the voltage dependent DRC rules. Can you specify more? What are the guidance when we design the non-default rules for the high voltage NAND? For example, my normal voltage is 1 volt. I have one high voltage NAND which is about 1.8 volts. When I design the non-default rules, what are the guidance? What kind of things we need to consider when we design the spacing?
So obviously you're looking at the devices itself. Can they handle the right? So the first point is your schematic, your circuit. Is it going to handle that capability? You have to be able to identify those circuit nodes that will see the elevated voltages, and identify those on the circuit so that you can simulate and verify the voltage. But then that identification that you use on the schematic side has to be translated to the layout accurately every time. You cannot have any mistakes. So you often tie that in with LVS flow to verify that you're placing the same voltage marker on those same circuit nodes in the layout as you are in the schematic. So all of it ties together. And when you get to the layout phase, you have design rules, just like any other metal layer or active or in-well spacings. You have to identify those circuit nodes that have that voltage designation, and then check the relationship of those layers to other layers that you care about. It can be the same level metal, and in some cases where they're higher elevated, you may care about the distance and relationship to the next layer above or the next layer below. So it all depends on how your voltage dependent spacing rules are laid out for that technology node, what you care about as the layout designer. But it can be quite complicated depending on how high your voltage gets. Does that answer your question, or are you looking for something?
For example, if my voltage is 2 volts, 3 volts, 5 volts, how we design the spacing, how we specify the spacing when we design the design rules?
Right, so that is just an additional rule. Raul showed the number of rules that you have in a rule deck. It's just one additional rule to everything that you have for can this design be manufactured. Now you're taking into that voltage account where it's not just manufacturer that you care about the lifetime of the device. How are those oxides between those layers going to hold up over the lifetime? So it's a reliability question that needs to be determined, what those spacing rules are for those voltage nets.
Yeah, my name is Asan Chaudhary. I'm in Samsung. I think, but just comment. I think it will come through the DAC for the designer. The fab DAC will automatically put those rules there.
Correct.
So if you run your DAC, and if you put the marker as you mentioned, it should catch that if you violate between the two nets, which is different voltage.
Right. That is designed by the fab
Yeah.
process
Yeah.
engineers.
Thank you.
Thanks.
Name and company, please.
So I'm Ethan Cohen from AMD. First question for any of you, I guess. You mentioned the explosion in DRC rules. Just wanted to know if you could touch on any potential solutions or methods to help designers deal with these. Designers and other folks who are handling the decks.
Raul? Oh, Raul didn't understand the question.
No, the first part of the question.
Oh, the first part of the question. Do you mind repeating your...
What?
So I just wanted to know if you could touch on any potential solutions that would help designers or anybody in the entire system that handles DRC decks to cope with the explosion of the DRC rules and the complexity as well.
Yeah, no, I thought you were referring to something specific, right? Yeah. Well, as I said, right, we think that the main mechanisms that you need to use to develop rules, right, are one, to cope with the complexity of the rules, and that has to do with being able to execute them. So if you design a rule, that becomes an executable in the sense that you can run your design rule check right away and keep changing the rules, right, and you can generate patterns that conform to the rule or that violate the rule, right, to sort of check if that is what you mean. Now, in more complicated cases, like what we're talking about here, right, like coloring and so on and so forth, that's not trivial, right? I mean, we try to develop, for example, a coverage measure for a rule, and sometimes if you wanna try many topologies, you rotate things and so on and so forth, right, and just vary a few variables, right, you get many thousands of patterns, right, that you have to run, inspect, and see if that is what you meant. But I think that is sort of the best shot at complexity right now. The other one is as you decompose. If you decompose things, sometimes things can get a little bit more simple, right? So if you know that things are colored, if you know that you have cut masks, and so on and so forth, right? You can check those, which is typically easier than checking the original artwork, which is what you get from your designer when things are not colored, and so on and so forth. So you're sort of splitting the problem. In terms of numbers, I don't think that is really a problem directly. It becomes a problem because of the interaction, right? So you never check a rule by itself. You're checking it in the context of all the other rules, right? And so picking what other rules should be fulfilled and not being violated when you're checking one rule, right, is a little bit tricky. But at the end of the day, I think the key thing is that you need to develop the things just like you develop everything else. Like you do a design with tools, you write software by executing it, checking it, testing it, writing test cases, right? The same methodology needs to apply to rules. They're complex enough today that you have to do it that way. You can't just write them down.
We have time for one or two more questions if you'd like to have a question. Well, go ahead, Marshall.
Marshall Tyner with SI2. Question for the whole panel. Where do you see the architecture of checking decks going? Will we go to massively parallel or multiple passes? Or what does it look like for the near term out there?
Who are you asking it
to? To the whole panel.
I think we're going to see multiple passes in a different form. It's going to be at the standard cell level, at the block level, at the chip integration level, and the cells that the rules that you're going to test at a cell level are going to be different than the rules you're going to test at the block level. There will be some overlap. I again tell you there are coloring concerns that if you try to solve them at the standard cell level, you're going to break them at the chip level, and vice versa. So some rules will have to be addressed at every level, but I think just because there are 10,000 rules, some of which, like I was pointing out, are not drawn, but are show up on silicon. There's just an inordinate amount of rules that you need to ask your layout engineers to be able to manipulate otherwise. So I think you'll have standard cell rules, you will have block rules, you will have chip rules.
Michael, Raul?
Yeah, I'd like to add to that, right? There's a bunch of other aspects which are interesting, right? One is that if you think of it, all interesting designs and IP get developed on a process that is not ready. You see, when the process comes out, you want to have the IP, you want to have the designs, right? And until the last day, you're still sort of twiggling with it and changing the rules. And so one problem, right, that you have to close is that there's a lot of decks, if you wish, that are not really ready, right? That sort of check the design, but they are not finished, and this rule's missing, and so on and so forth. And that is also a problem that we address, and because we think that is very important, right? You need to be able to change a rule and see the effect on the design right away. You wanna go beyond just checking. You also wanna see the sensitivity to a rule. If you know that there's a particular rule that has most effect on your silicon real estate, you want to know what is the sensitivity. Can we relax that rule a little bit? Can we relax it a lot? Are there trade-offs and so on and so forth? And all that works if you're more or less interactive. The moment you change a rule, you don't have to go through all kinds of different steps to generate a deck and then test the deck, and that takes weeks, right? And then you get to another iteration. You want to be able to do that more or less right away. From the moment you check it in your system, you get a checker, particularly while you're developing the process and you're developing the IP. So I think that's one thing, right? And the other thing, I think you mentioned parallel, right? Just from a computational point of view, I think that is sort of already there, right? All these checkers run in parallel, and I think that you'll see that just accelerating, because turnaround time is important, right? And then there is, of course, the in-design rule check versus a sign-off in the end, which is always, it contains a lot of stuff that perhaps is not exposed to the designer, right? Hidden things and so on and so forth, that is done more by the fab. So there is no one check, right? There's a lot of different checks, right?
Absolutely.
As we're pointing out.
Yeah, I do. I see that there is a need for when you're doing the routing in your standard cell or your IP block. I do see that there is a need for real-time checking of your rules as you're drawing those specific layers. I think that is the first step to helping the cycle, or closing the loop on getting your design rule clean, your design clean to the rules, just to be able to draw those at the front that'll be clean. And then you'll do more in-depth checking between all the different coloring rules that need to be applied. And then, like you say, with the standard cells, when you place those next to other standard cells, you're going to see some new issues that you didn't even consider when you were designing that cell the first time. Boundary kind of conditions with your cells. Of course, you also always have the routing considerations. Are you going to route over this IP block? What are the things that those route over layers have to do with the design rules that you care about for those boundaries? It's a multiple pass DRC checking that needs to be happening.
We have time for exactly one more question, if we have one more. Well, with that, I'd like to thank the panel. Could we give a round of applause to our panelists?